Hi, everyone. Thank you for joining us for this session on best practices for data streaming with Amazon Kinesis data streams. My name is Karthi Thiagarajan, and I'm a solutions architect on the Amazon Kinesis team. Here's the agenda for today's session, and we'll use a scenario-based approach for talking about these best practices, and we'll cover 5 broad scenarios. And the theme that we'll use throughout this session will be latency and throughput. Before we jump into the first best practice, let's do a quick overview of Amazon Kinesis data streams. Now, a key detail to note about Amazon Kinesis data streams is that you don't provision servers or VMs or containers in order to do ingestion and stream processing. You provision something known as a stream, and you interact with this stream using our APIs. Now, within a stream, the unit of scale that you'll be working with is known as a shard. And each shard can support 1 megabyte per second of ingest as well as 1,000 transactions per second. And on the egress side, a shard can give you 2 megabytes per second of egress and 5 transactions per second. Something to keep in mind when you're publishing data to a Kinesis data stream is that you have to specify a partition key. This partition key helps Kinesis data streams essentially bucket the incoming data into the available shards. So you want to make sure that you choose a partition key that results in a uniform data distribution across the available shards. Now, when we went over the consumption limits per shard, if you feel that you need more consumption capacity per shard, then you'll be happy to learn that you can use something known as enhanced fanout, also abbreviated to EFO. With enhanced fanout, each of the consumers that you register as enhanced fanout can actually support a dedicated 2 megabyte per second pipe. And over this pipe, Kinesis data streams will deliver data to you, to your consumer, via a long-lived HTTP2 connection. And you can have up to 20 enhanced fanout consumers. And in addition to significantly increasing the consumption throughput per shard, enhanced fanout will also give you great end-to-end latency, 70 milliseconds or better. Now, this is compared to a floor of roughly 200 milliseconds when using consumers that are not enhanced fanout. Okay, with that background about Kinesis data streams, let's consider a scenario where you've set up a stream processing pipeline that's shown in this diagram. You're collecting clickstream data from various screens, like mobile devices, web apps, desktops, etc. And you're ingesting this data via an Amazon Kinesis data stream into Amazon Elasticsearch. And let's say you're going to use this data to do real-time recommendations for your e-commerce site. You've set this up, and as a good architect, you've also made sure to retain 5 days of data in your Kinesis data stream. And you did this because you know that the first streaming use case that you can think of is rarely the only one that will be driven off of this ingested data. Here I should mention real quick that a Kinesis data stream by default is set up to retain 24 hours of data. With that said, we recently released a feature known as long-term retention for Amazon Kinesis data streams that will let you retain up to a year's worth of data. Now, for this scenario, we'll stick with 5 days because, as you'll see, it'll make the arithmetic easier when we talk about increasing the consumption throughput. It is fortunate, by the way, that you've decided to retain 5 days worth of data because the fraud detection department in your organization approaches you with an architecture they'd like to implement for detecting nefarious bots, nefarious users. And so what they'd like you to do is use the existing or the retained data in your Kinesis data stream to train a fraud detection model. Now here's where consumption throughput or increased consumption throughput really comes in handy. And you'll see how enhanced fan-out can help here. In this illustration, the first thing I'll mention is, for the sake of discussions and to keep the arithmetic simpler, let's assume a single shard. And what we're going to do is divvy up the 5 days worth of data in that shard into 5 time slices, conveniently working out to 5 days. And each time slice, therefore, is a single day. And as you can see here, each enhanced fan-out consumer will be assigned to its own time slice. So what you get is data being read in parallel at a rate of 2 megabytes per second per consumer, working out to a total of 10 megabytes per second. So this allows us to draw down on the retained data much more quickly so that it can then be used to train our fraud detection model. Let's dive a bit deeper into the arithmetic so we can see the time savings involved. Once again, we have a single shard, and as we discussed before, on the ingress side, we have data being ingested at a rate of 1 megabyte per second. And that took us 5 days, assuming that data was coming in at the maximum possible ingest rate. If we then use a single consumer, whether it's enhanced fan-out or not, then we get an egress rate of 2 megabytes, and that will take us roughly half the time it took to ingest, which is around 2.5 days. It's better, but we can do even better than that. So with 10 enhanced fan-out consumers, we get a total rate of 20 megabytes per second for a single shard. So do keep that in mind. And that works out to a total of 6 hours to drain 5 days worth of data. And as you can probably calculate yourself, with up to 20 enhanced fan-out consumers, you can reduce the drawdown time all the way to 3 hours. So hopefully that gives you an idea of what using multiple enhanced fan-out consumers gives you. Now, a couple of quick points to keep in mind. You can use either something like Apache Flink or a Kinesis client library application. Each of these we'll talk about in more detail, but not in this context. The other thing I want to mention is you want to make sure that you're accounting for duplicates, any overlaps across these time slices. We won't cover that because we don't have the time to do so, but I would recommend that you ensure that anything that happens downstream from drawing down on the stream is idempotent so that you don't have to worry about small overlaps in consumption across these time slices. That brings us to scenario number 2. AWS Lambda, as most of you may already know, is a popular way to consume data from a Kinesis data stream and also to do stream processing. It's popular for a few reasons. The first one is that simply by combining Kinesis data streams and Lambda, you get a fully serverless setup for ingesting and processing streaming data. You don't have to worry about setting up servers or containers or anything like that, even on the stream processing side. And once you've set up a Lambda function as a trigger, a Kinesis data stream as a trigger for your Lambda function, then the native Kinesis Lambda integration, this is something that the Lambda team has built, gives you, or actually invokes, one Lambda function per shard. This is the default behavior. As we'll see, we have some options for tweaking this based on our processing needs. And lastly, I'll mention that another reason why AWS Lambda is extremely popular for consuming from a Kinesis data stream is that you can write your processing logic in one of the many languages that is supported by AWS Lambda. Python, C#, Java, and Node.js, just to name a few. Let's first look at the knobs that we can tweak to optimize for throughput. As I mentioned on the previous slide, the Kinesis Lambda integration maps each shard to an instance of your Lambda function by default. Now, if you notice that you need more consumption or processing power, if that ends up being the bottleneck, then you can actually turn to something known as the parallelization factor. By default, the parallelization factor is 1. You can turn it all the way up to 10. And what the parallelization factor lets you do is for each shard, you can actually have the Kinesis Lambda integration spin up more than one parallel invocation of your Lambda. So this gives you additional processing power because each of those instances of your Lambda function per shard are actually handed separate records. And so you get this parallelization. And we'll actually see how this can still preserve ordering in a couple of slides. Okay, the next two settings after parallelization factor have ramifications for both latency and throughput. And on the throughput side, you can increase batch size to its highest value, 10,000 records, to a limit of 6 megabytes. And batch window can be as high as 300 seconds. And it should be intuitive that by increasing both batch size and batch window to their highest values, you're actually optimizing for throughput. And as we'll see, it's the inverse for when you need to optimize for latency. So far, the settings we've discussed on this slide have to do with optimizing for throughput within a single application. And it should come as no surprise, based on our last scenario, that if you want to increase consumption throughput across multiple consumers, you would use enhanced fanout, all the way up to 40 megabytes per second for a single shard by using up to 20 enhanced fanout consumers. Okay, on the latency side, the number one thing I recommend you do if you have a latency-sensitive application when using Lambda is that you register your consumer as an enhanced fanout consumer. The native Kinesis Lambda integration does polling on your behalf from the source stream and delivers messages to you. When you're not using enhanced fanout, this polling interval is fixed at 1 second. So that's the floor when using Lambda for end-to-end latency. Whereas when you use enhanced fanout, that latency can be as low as 70 milliseconds or better. So that's a no-brainer when it comes to optimizing for latency with Lambda. And as I mentioned in the last slide, both batch size and batch window should be set to their lowest values if you have a latency-sensitive application. That way, the Kinesis Lambda integration hands batches of records much more quickly to your Lambda invocations. And lastly, if you want to reduce the Lambda startup time, then you can actually use something called provision concurrency. This is a capability that is available in AWS Lambda. Before we wrap up this best practice, a quick note on ordering when using parallelization factor. We've already talked about partition key. There's another characteristic associated with messages that are being ingested into a Kinesis stream known as sequence number. Sequence numbers increase monotonically as records are ingested into Kinesis at a shard level. And this is what signifies order within a shard. So imagine a scenario where you've set parallelization factor to 2 and you have a single shard. And as records are being delivered to instances of your Lambda function, in this case 2 instances, what the Kinesis Lambda integration will do is group messages by partition key and then maintain order by sequence number. So as an example, if you have clickstream data marked with customer ID as the partition key, you can see how messages for a customer, clickstream messages for a customer, will then be ordered in the order that they were ingested, grouped by customer ID. Okay, on to number 3. A common question we get asked is, how do I decide on the best consumption strategy? So in order to answer that question, what we'll do is we'll focus on 3 popular scenarios. And this is not meant to be comprehensive, but I wanted to bring up three options that are popular. We've already seen AWS Lambda. Option number 2 is Amazon Kinesis Data Analytics for Apache Flink. And the third option is Kinesis Client Library, or KCL, applications. Apache Flink is a modern open source framework to help you build stream processing applications. And our AWS service, Amazon Kinesis Data Analytics for Apache Flink, is a fully managed service that lets you run Flink applications. And the Kinesis Client Library is a framework that the Amazon Kinesis team released to help you write scalable and highly performant applications. So on the next slide, we'll actually combine these three options along with the key characteristics that you should keep in mind to help you decide on the best strategy for your needs. And here's that matrix. So you've got 3 rows, each representing the 3 options we talked about. And then on the columns, we have the characteristics that I mentioned. The first one that we'll consider is latency as it pertains to non-EFO consumers. With enhanced fanout, it's a no-brainer. You get 70 milliseconds of latency or better with all 3 options. Now, when you're building consumers with these options, these 3 options, and you're using a non-enhanced fanout consumer, with Lambda, as you saw, the latency is 1 millisecond or better because of the polling interval. With the other 2 options, Flink and KCL, you actually have more fine-grained control, and you can change the polling interval to as low as 200 milliseconds. This, by the way, is a constraint that you saw when we talked about what a single shard can support in terms of transactions per second on the egress side. Now, there are many applications. For most applications, you actually only care about consuming from a single data source. If that's the case, then all 3 options will work without any challenges. Now, if you want to read from multiple sources, then Flink gives you support for pulling in data from multiple sources, whether they be Kinesis or some other source like Kafka. Whereas with KCL, you can now read from multiple Kinesis streams, no problem. The last 3 columns are something that really lets Apache Flink stand out. So you get stateful processing, exactly once processing, and an expressive API to do stream processing with Apache Flink. You get this out of the box, it's built in. Whereas with Lambda and KCL, you kind of have to provide these capabilities on your own. You could use an external database service like Dynamo and build in exactly once capability and stateful processing capability. Before we touch on scenario number 4, a quick recap of what Kinesis Data Analytics for Apache Flink is. We already saw how it's a fully managed service for running Apache Flink applications. It can actually also support running Apache Beam applications. And both of these are modern open source frameworks for doing stream processing. And I should mention also batch. But since our focus is on stream processing, I figured I'd mention that. And they also come with support out of the box to do stateful processing and exactly once processing. And another reason for their popularity is they have support for a variety of connectors. Amazon S3, Amazon Kinesis, Kafka, and just to name a few. All right, with that background, let's look at autoscaling. Should go without saying that autoscaling and throughput go hand in hand. So when your throughput needs, change on the stream ingestion front, you often have to adjust your processing throughput or processing capability as well. So, for example, let's say you have a Kinesis data stream that you have set up to, change the number of shards based on incoming throughput. And you have a Kinesis Data Analytics for Apache Flink application consuming from this Kinesis data stream. By default, you can take advantage of the CPU-based autoscaling that is built into Amazon Kinesis Data Analytics for Apache Flink. So what this means is the service the service being our managed Amazon Kinesis Data Analytics for Apache Flink service, will detect if the CPU usage across your processing units, also known as Kinesis processing units, is at 75% or higher for an extended period of time. It will automatically increase the parallelism. And then it will do the inverse when processing needs decrease. This works for many scenarios. However, not all applications are CPU bound. So if you want to set up autoscaling based on either throughput on the incoming stream or something known as a behindedness metric, like millis behind latest for Kinesis or lag in Kafka, you can use our AWS application autoscaling service to do this. So let's look at the throughput-based scaling strategy initially. For this, we'll use a type of autoscaling policy known as step scaling. And it's very straightforward. As you can see in this illustration, we essentially specify ranges of incoming throughput. In this case, 200 to 1500 having a parallelism of 8, and throughput of 1500 to 1000 with a parallelism of 6. And we can do this for a number of ranges, and we can also specify a ceiling and a floor. So you can see that step scaling based autoscaling is very straightforward. Next up is a target tracking autoscaling policy. What this lets us do is, based on our behindedness metric, we set up a threshold. We want our behindedness metric to be no less than 60 seconds. So if that behindedness metric goes above 60 seconds, then we will provision more consumption resources, more Kinesis processing units. And this is actually something that we can essentially encode in the target tracking autoscaling policy. And if you're wondering how you can do this, we actually released a blog post that goes into more detail, as well as a sample. The sample covers both step scaling and target tracking based scaling. So I'd recommend that you check these two links out for more information. Okay, so we're now at the last best practice. And as before, I want to spend a little bit of time providing context before we jump into our scenario. And the service in focus for this scenario is Kinesis Data Firehose. And this service gives you a no-code way to ingest data and then deliver that data to a variety of destinations. You can see AWS services here along with partner services. I've mentioned Splunk, but we also support delivery, native delivery to Datadog, New Relic, and Sumo Logic. I mentioned no code a little while ago, but do keep in mind that you can supply transformation logic as an AWS Lambda function if you'd like to transform records after they've been ingested and before they're delivered to one of these destinations. On the ingestion side, you can either directly publish from one or more sources into Kinesis Data Firehose, or you can use an intermediate Kinesis data stream as shown in this diagram. And we'll actually look at where you would want to do this and why you would want to do this in a couple of slides. So first, let's talk about latency. Philosophically, I should mention that Kinesis Data Firehose was designed to make it easy for you to ingest and deliver data. So the latency adjustments we talk about here are more coarse-grained, and you have two options, buffer size and buffer interval, and both of them, as you can imagine, have to do with buffering of data before delivery to one of the destinations I just mentioned. If you set these settings to their lowest values, then you can imagine how latency is reduced. With that said, I should emphasize that if you want latency to be in the single-digit seconds or lower, then I would recommend that you use Kinesis data streams along with one of the processing options I mentioned earlier. And you can actually look at the settings associated with these two buffer size and buffer interval in the link that I've included in this slide deck. So let's look at throughput. As I mentioned, Kinesis Data Firehose is designed to make it easy for you to ingest data. And in keeping with that philosophy, the service automatically scales its internal resources based on the throughput that it sees. When you're using the direct put approach, the limits associated, for ingestion with your Kinesis Data Firehose delivery stream are very high. Now, there are customers who will want to request limit raises via quota increases, and those limits vary from region to region. So once again, I'd recommend that you check out that link on this slide to get more details. Now, beyond direct put, if your throughput needs are even higher, even after quota increases, then I would recommend that you use an intermediate Kinesis data stream. With this approach, you actually publish to that intermediate Kinesis stream from one or more of your sources, and you have to manage the number of shards that that stream is provisioned with based on your throughput needs. And then the downstream Kinesis Data Firehose delivery stream automatically adjusts its resources based on this upstream Kinesis data stream. So that brings us to the end of our list of best practices. And we'll do a quick summary. So first, we saw how you can do efficient catch-up processing in a much more throughput optimized fashion by using multiple enhanced fan-out consumers. Then we saw how to use various knobs for tuning both latency and throughput when using AWS Lambda to consume from Kinesis data streams. After that, we looked at the key characteristics to keep in mind when deciding on a consumption strategy between AWS Lambda, Amazon Kinesis Data Analytics for Apache Flink, and Kinesis Client Library. And then we discussed auto-scaling approaches to keep in mind when using Amazon Kinesis Data Analytics for Apache Flink. And then we wrap things up with a discussion of how to tune your Kinesis Data Firehose delivery streams. Thanks again for watching this session, and enjoy the rest of reInvent 2020.